Hello, my name is Andrew, and today I'll be doing a brief overview video of Project 1. Now, before I begin, I do want to mention that this video should not be used as a substitute for actually reading the specs in their entirety. The specs do contain many important details that you have to fully understand to get full credit, so please do read the specs and don't just rely on this. However, hopefully this video will be enough to provide you with, a brief overview of what the project is asking you to do, kind of like a big idea, so you can get started as soon as possible and come to us if you need any help. So, what is the goal of this project? So in this project, you're going to be a guide for a pirate ship in their quest for treasure. So there's a pirate ship out there at a certain location, and they're in search of some treasure that is nearby. But they don't know where this treasure is, and they have hired you to help them discover a path from where they currently are to where the treasure is located. Luckily for you, you have access to a map of the nearby surroundings, and this map will be given to you in the form of either a map or a list in your input file. And we'll cover this later when I talk about input files. But essentially you'll be given a map of the surrounding area, and this map will be identified using symbols that represent different types of terrain. So here's an example map that you might be given. Here's a 6x6 map that I've numbered with the rows and columns. These numbers won't actually be in the input file. They're just here to make things easier to look at. But essentially the map will contain a sequence of characters in the form of either a period, which represents water, a lowercase o, which represents land, a pound symbol, which represents an impassable tile, and an @ symbol to represent your current location, and the $sign to represent the location of the treasure. And your goal here with this project is to be able to discover a path from the current location, which is this @ symbol, to this $sign. Now you might be asking, well, there are many different paths that I can take from the @ symbol to $sign, right? I could, for example, go up and take this path, and that leads me to the treasure. Or I can go somewhere else and take this path down here and go up to the treasure, right? How do I know which one is the correct one to output? Well, it's a bit more than actually returning a path. You have to return the correct path, and the path is determined using the routing scheme. And essentially the routing scheme is the algorithm that we used to determine how to move in this map. So there are two different types of routing schemes or searching algorithms that we'll be using in this project. Searching using a stack or stack mode, and searching using a queue or queue mode. Here's a very brief overview of what these modes are kind of like. These aren't fully detailed, but hopefully this will be kind of a very brief detail how to do this. So stack mode essentially is kind of like traveling down each path individually and looking for the treasure, right? So for example here, if we're in the @ symbol, we could be going around paths around us and checking for the treasure along different paths until we find the treasure. Think of this as kind of, if you want to find something, you first look down one, row, and then if the treasure is not there, you come back and you look in a different row, and you come back and you look in a different row. Stack mode is kind of like that, traveling down each path individually to check for the treasure. While queue mode is kind of expanding the search, right? So here's an example with queue mode. If you're here and you want to find the treasure located here, you might end up with something like this, where you start and basically you scour the area around you until you find the treasure. So looking at, in a circular, expanding the radii of this search area until you hit the treasure, right? So unlike stack mode where you look down each path one by one, in queue mode you are, expanding the search area. So this is not, a full explanation of how these methods work, but this is just kind of like a very basic explanation of what you should expect with these two methods. Now, why are they called stack and queue? Well, they're called stack and queue because they're implemented using two different types of containers called stacks and queues. And you've probably learned in lecture already that a stack and a queue are essentially containers that allow access to elements in very different ways. Right, so in a queue, for example, the element that you're able to access next in the queue is the element that has been in the queue the longest. So think about like an office hours queue, for example. The student who is next to be helped is the student that has been in the queue the longest. Meanwhile, a stack, the next element that you can access is the element that you most recently put in. So think about a stack of books, for example, where if you stack a bunch of books in a large pile, the next book that you can access is the book at the very top of the stack. And that book must have been the one you put on most recently. And this kind of forms the basis of how we actually explore the map, right? So suppose we are here, right? We are currently at this @ symbol here at position 50 in this map. And we want to determine how to look next, right? So the difference between these two paths is that the path up here starts at position 50 and moves up to position 40 as the next, element in the path. Well, this path down here, which is equally valid, instead of moving up to 40, takes a right to 51. Now, how do we know which one to go? Should we go up or should we go right? If both cases, these are valid. And this is determined using the container that we use, right? So suppose we add position 40 to the map, and then we add position 51 to the map, right? And if we use a queue, right, we would say, okay, we added 40 first. So that means we would visit 40 first. Well, if we use a stack, we would say we added 51 most recently, so we should look at 51. And because the order in which we visit tiles can differ greatly depending on which tile we visit next, right? And the tile we visit next is very different in the queue and a stack. The two different methods can lead to two very different paths, right? If you use a queue, for example, one path might be valid, but if you use a stack, it might give you an entirely new path. So this is kind of just an overview of how to use these two methods, and now let's go through an actual example. So depending on the search algorithm that you're actually using, the path that you'll produce can be very different. And to show this, I'll go through an example using both a stack and a queue as the container that we use to discover nearby elements. So first of all, here is the actual specs. This is the algorithm we actually give you, and I've copied this over from the specs document itself. But I'll be going through an example visually using both the stack and the queue using this example map here. Now before I begin, I do want to mention something I didn't mention previously, is that there are two people in the boat. There's the captain and there's the first mate. The captain is essentially responsible for sailing through water locations, while the first mate is responsible for looking through land. Now on this map, we don't actually have any land positions or land, characters, the lowercase o. So we don't actually really use the first mate here, but we'll go through an example later on that, includes both water and land positions. So let's look at how we go through this map using the hunt algorithm. And first, we'll use a stack to show this. Let's go through a stack first. So in the stack algorithm, the next element that you want to consider is the element that has been most recently added. So we'll go through this example here. So with a stack, the first step, actually with both a stack and a queue, is to first seed your container. So here's my stack. Suppose here's my stack container, where this is the top of the stack, this is the bottom of the stack, and I add elements this way. Right, so first I'm at 50, so I'm going to add 50 here to the bottom of the stack. And then what I'm going to do is I'm going to continue an algorithm over and over and over again until the stack is empty. And that's going to be the searching algorithm. So this algorithm is as follows. I'm going to take the next element off the stack and assign it to the current tile that I am looking at. So in this case, 50 is the only element here, so 50 gets set as current. Then I'm going to go through all adjacent elements to 50 and add them in the following specified order into the stack container. So I'm currently at 50. I'm going to add the element adjacent to the north, east, south, and west to this container under two conditions. First, that the tile actually exists and can be accessed. So for example, here, there's really no tile to the south of us, right? So south doesn't get added. You don't add 60 because there is no 60. And also another case is, these pound symbols, right? You don't add them to the stack, right? You can't actually visit this tile because it's impassable. So first it has to be something you can access. And second, it must be something that you haven't visited already. And we'll go through this in more detail as we go through the example. But the reason why we don't want to do this is because that would cause us to, visit the same tile over and over and over again. And if we know a tile works, or if it doesn't, we don't have to check again, right? That's just going to get us stuck in an infinite loop, and we don't want that to happen. So let's go through this algorithm. We're currently looking at 5, 0. We're going to add elements to north, to the east, the south, the west to our stack. So currently we have 5, 0. And we look to north, we say, okay, we have 4, 0. 4, 0 is a valid block that hasn't been visited already. So I'm going to add 4, 0 to the stack. East is 5, 1. 5, 1 is fine, so I add 5, 1 to the stack. South and west don't exist, so there's nothing to be added. So after this, we look to see if the stack is empty. If the stack is empty, we're done. But it's not, because there's still 2 elements. So what we're going to do is we're going to take the top element off the stack. In this case, it's 5, 1. I'm going to fix this here, 5, 1, and I'm going to set this as my new current. Right. So notice here, 5, 0, we added 4, 0, and 5, 1. Now we're looking at 5, 1, because this is the most recent tile that we added to the stack. And we're going to do the same process. We're going to check the north, east, south, and west to see if we visited an element before, and if we haven't, we're going to add it. So in this case, we'll look to the north, we see 4, 1. 4, 1 hasn't been visited yet, so we add 4, 1 to our stack. To the right, we have 5, 2. 5, 2 is an impassable block, so we don't add it because we can't visit it at all. And then south and west, well, south doesn't exist, and west is our starting position. We've already visited it before, so we don't need to add it again. So in this case, the only element that gets added here when considering 5, 1 is 4, 1. Alright, is the stack empty? No, it's not. Let's continue the process. We're going to take the top element off the stack again, which is 4, 1. Set this as our current, and we're going to start looking from here. 4, 1. Well, we can't look to the north. We say 3, 1. That's an impassable block. We ignore it. 4, 2. That's fine to add, so I'm going to add 4, 2 into our stack. South, we already visited this before. West, 4, 0 has been visited before, so the only element that gets added here is 4, 2. Not empty, so we're going to take out the top element in our stack. So this is our current. Start from 4, 2, add the valid elements. So in this case, we have 3, 2, and 4, 3 as the 2 elements that can be added. So we're going to add 3, 2, and 4, 3 to our stack. Stack is not empty, search is not over. So we're going to take the top element off our stack, 4, 3, set this as our current element, 4, 3, and continue the search. We're going to add 4, 3, we're going to add 3, 3, we ignore 4, 4, and we're going to add 5, 3. So we're going to add these 2 to our stack, 3, 3, and 5, 3. Stack's not empty, search continues. 5, 3 gets set as our current element that we're considering. We're going to look at 5, 3, which is this one here. North, 4, 3 has been visited already. 5, 4 hasn't, so we're going to add a 5, 4 to our stack. There's nothing to the south, and the west is we have an impassable block, so we ignore it. Search is not empty. We take 5, 4, set this as our current. You can see the process right now is basically we just take the top element off, add any adjacent elements that we can visit to our stack in the search order we have, and continue this process until we either have an empty container or we find the treasure. Right, so I'm just going to go through this by hand, but I'm not really going to talk about each individual item. I'm just going to do this, manually here. But hopefully you can follow along. We have 4, 5 here, right? 4, 5, we look, we add 3, 5, that's the only thing we add. So we can add 3, 5, take 3, 5 off, put 3, 5 here, right? 3, 5. We can get the 2, 5, so 2, 5 gets added, nothing else, so 2, 5 is the next element. 2, 5 gets added. 2, 5 we can add 1, 5, and we can also add 2, 4. 1, 5 is north, so it gets added first. 2, 4 is west, so it gets added second. The next element off the stack is now 2, 4, so I'm going to take 2, 4. So this is my current. 2, 4 really can't add anything because both, all the north, west, and south are impassable blocks, and east has already been visited, so we essentially don't have anything for this, and we just take off the next element on the stack. So here we go, 2, 4 then now becomes 1, 5. 1, 5 is this position. We can look to north, we can add 0, 5. But wait, 0, 5 here is the $sign, so we've already found the treasure, which means that we have a path, right? 0, 5 is the location we want to find. So we're done. We stop the search right here, and now we say, okay, our path is, this one here. So we go up like this, and we go down, and then we go up. And I'll go through how to actually find this path in a later example. But this is the path we end up getting using this algorithm. So that's stack version. Now let's look through the queue. Right? So the queue is similar, except for instead of taking this element off, because that's the most recently added element, in the queue we take off the element that's been here the longest. So 40 will be visited instead of the whatever element's at the top. So let's go through this example again, but with a queue, and see how the result is different. Alright, now same example, this time using a queue instead of a stack. So let's see how this path is different. Right, so in the queue, instead of, visiting elements based on the most recently added element, we look at the element that's been in the queue the longest as our next element. So let's go through this again. So we have a queue. We're going to start here at our current position, which is 50. We're going to seed the container. We're going to add 50 to our queue. Then, as long as the queue is not empty or if the treasure is not found, we're going to continue the following over and over again. We're going to take out the front element of the queue, or the element that's been in the queue the longest, set it as the current element we're visiting, and then we're going to add adjacent elements to this current element in this search order to our queue. So here we have 50, we're going to go north, we're going to add 40, then we're going to go east and add 51, and those are the only two we can add, so we're going to add these two to our queue. Now, the queue is not empty, the treasure hasn't been found yet, so I'm going to take the front element here, which is actually 40, and I'm going to put 40 as my current. Now I'm going to start at 40, add elements in the order NESW. We're going to go north, we can add 30, so we're going to add 30 to our container. And then we're going to add 41 here. So 41 is going to be our next element that we added. This @ symbol has been visited already, so we don't look at it again. And that's it. There's nothing to the left. So 30 and 41 get added as a result of considering 40. Now the queue is not empty and the search is not over. So now we're going to consider 51. What do we add from 51? Well, we are currently at 51 here. We look to the north. We're going to say, okay, 41 has already been visited, so I'm not going to add it again. 52 has this impassable block, so that gets ignored. There's nothing to the south, and the starting position has been visited already. So 51 actually doesn't add anything to our queue. So we just pop off the next element, which is 30. We look at 30, we say, okay, 30 here. We look to the north, can we add 20? Yes, we can, so we're going to go and add 20. Look to the right, we have this impassable block, so we ignore it. South has been visited already, and there's nothing to the west. So we added 20, and that's the result of looking at 30. So we're done with 30, we take off the next element off the queue, which is 41. We look at 41, look to the north, we can't add that. We can, however, add 42, so 42 gets added to our queue. Look below, 51 has been visited already, 40 has been visited already, so we don't consider those. Next off, queue is still not empty, so we're going to add 20 to our current element list. 20 is right here, we look to the north, we can add 10, so 10 gets added. Sorry, and my board, give me a second, move to the line. So 10 here gets added, we're going to look to the right, we're going to say, okay, 21 is also not visited, so we add that as well. South hasn't visited already, west there is nothing, so we're done there. Queue is not empty, treasure hasn't found, so we take off the next element and look at that, which is 42. We go to 42, which is here, we add 32, because that hasn't visited already, and then we add 43, that hasn't visited already. Nothing to the south, nothing to the west. We're done here, we look at the next element, 10, we take this off the queue. 10, we look to the north, we can add 0, we look to the right, we can add 1. South hasn't visited, and there's nothing to the west, so we're done there. I'm going to move this down lower so we can add more elements to our queue, but after we look at 10, we're going to look at 21. So look at 21 here, that's a current, we take this off the queue, we look at 21. We can't add 1 because it's already been visited, but we can, however, add 2. So 2 goes in here. Nothing to the south, nothing to the west, so we're done with 21. Queue's not empty, treasure hasn't found, so we pop up the next element of the queue, which is 32. We look at 32 here. We can't add 22 because it's already visited, but we can add 33. So 33 gets added, nothing to the south, west is impassable, so we're done there. Queue is not empty, treasure hasn't found, so we're going to take off the next element of the queue, which is 43. 43 comes off the queue, 43 is here, north hasn't visited, east is impassable, south, however, can be added, so we're going to add 53 down here. And after we add 53, we go to the west, that's what it did, so we are done for 43, we'll take off 43. Next one on the queue is 00. 0, 0 is here. North, there's nothing. East, we have 0, 1, so 0, 1 gets added to Q. South and west, nothing there. Q still empty, treasure hasn't found, so we take off the next element that has our current. 1, 1, which is here. North has been visited already. Next element is 1, 2 that hasn't been visited yet, so that's going to be added to our Q. Nothing to the south, nothing to the west. Q is not empty, treasure hasn't found, so we're going to continue on. And we're going to continue doing this until we either find the treasure or our Q becomes empty. If the Q becomes empty, that indicates that the treasure hasn't been found and there's no valid path from the @ symbol to the $sign, in which there will be no solution. Let's continue here. We have 2, 2, nothing here. We can't. This is actually wrong row here. 2, 2 here, nothing to the north, nothing to the east, nothing to the south, nothing to the west. So we're done with 2, 2. Same thing with 3, 3. Notice here that everything adjacent to 3, 3 is either past 4 hasn't visited already, so 3 doesn't really add anything to our Q. Now we're going to have 5, 3. 5, 3 is here. We can add this element here, which will be next, so we're going to add 5, 4. 5, 4 gets added. Nothing else needed here, so 5, 3 is done. Now we're going to set to 0, 1. 0, 1 is here. Nothing to be added. North, there's nothing. East, there's some paths, south and west. Nothing here, so we're going to remove 0, 1. Now we're going to add 1, 2 to our Q. 1, 2 is here. Valid here is 1, 3, so 1, 3 gets added to our Q. Nothing else can be added, so we're done there. Next element here is 5, 4. So 5, 4 is here. We can add 5, 5 by looking to the right, but everything else is not able to be added, so we're done with that. 1, 3 is next. We'll look at 1, 3. 1, 3 is here. We can add 0, 3, but nothing else, because everything else hasn't visited already or is impassable. So we remove 1, 3. Next is 5, 5. 5, 5, we can add 5, 4. Nothing else, so we're done with that. 5, 5 is done. We can add 0, 3. 0, 3, we can add 0, 4. So that gets added to our Q. Nothing else is left for this, so we get rid of this. 5, 4 is next on our Q. We can add 3. It's actually not 5, 4. This is actually 4, 5. Sorry about that. 4, 5. 4, 5. 4, 5. We can add 3, 5. 3, 5 goes in our Q. Nothing else to be added, so we're done with 4, 4, 5. Next we have 0, 4. 0, 4, we can add 0, 5. Wait, that's the treasure, so we're done. So we don't even have to add 0, 5 to our Q. We can say, okay, we're done. We found our treasure, and now we have to find our way back. So similar to the stack example, how do we actually find the way back, right? We calculated all this stuff, and there's a reason why I draw all these arrows. It's not just to keep track of, which element has been visited already, but also so we can find our way back to the beginning. And this is something called back tracing. So what do we do in back tracing? Well, in back tracing, we're essentially taking this final destination that we have here, which is the $sign, and we want to find our way back to where we began, right? So we looked at all these positions here in the queue, right? So these are all the elements that we've seen, right? And these are a lot, but how do we know how we actually got here, right? And that is, you can notice here from the arrows, we can tell where each tile came from. So notice here we are currently at position 0, 5. We know that because this arrow here is pointing to the right, that we got to 0, 5 from 0, 4, right? And we got to 0, 4 from 0, 3. And we got to 0, 3 from 1, 3. And as we go through this, we can actually trace our way back to the beginning. And we say, okay, we finally ended here at 0, 5. We got to 0, 5 from 0, 4. We got to 0, 4 from 0, 3. Got to 0, 3 from 1, 3. And so on. We can essentially follow this back to our starting position. And that gives us the final path. So in this search algorithm, we essentially follow this arrow up, turn right, go up, and turn right again. And that's how we end up with our final position. So notice here, this is our Q example. We ended up traveling this way. With our stack, which you can go back and look at, we actually ended up traveling this way. We went to the bottom and we came all the way up, right? So these are the two different kind of solutions that you can get based on how you visit elements, whether you visit the most recently added element first or you visit the element that's been in your container the longest. And those are two solutions that can show up. Now, in this example, we don't have any land. And land actually complicates things because now we have to do two different searching algorithms at the same time. So, as we mentioned before, we have a captain. Captain only deals with water. So in this case, we all have water, so we're fine. The captain isn't really in charge of the whole thing. The captain is pretty much doing the whole work here and going through the searching algorithm on water. But in the case that there is land, we have to do two searches at the same time. Right? So the first mate goes through and looks through land. So the first mate has its own searching algorithm that determines which elements on land to visit next. So let's go through an example with both water and land to show how this works. So we're going to go through an example with land, but in this case I'm going to make my map a bit smaller just so we can save a bit of work on actually going through the algorithm. So we're going to have a 4x4 map here with 0, 1, 2, 3 as the rows and 0, 1, 2, 3 as the columns, right? And we're going to have this orientation here. We have water, water, land, treasure, water, 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 land, water, land, land, water, and current position, land, water, and water. So essentially what we have here is we essentially have two little islands here, one over here and one over here. And these two islands are essentially in our map, where this island contains the treasure and this island contains nothing. So how it's different from looking at all water? Well, previously, in the all water case, we were able to have one container for, the captain. So let's look at the queue, for example. We could have one queue for the captain, do our search with the same queue, find our way to the treasure, and that should be it. But in the case of land, we also have to consider the first mate, because the first mate is responsible for land exploration. The captain does not do any of this stuff. So the rules are as follows. First mate doesn't have to use the same container type, right? So the captain can use a queue, while the first mate can use a stack, and vice versa. Both can use a queue, both can also use a stack, and that's something that will be specified in the command line. But let's go through an example here. For the sake of simplicity, let's suppose both the captain and the queue, captain and the first mate, use queues to determine which location to visit next. Right, so let's start here. We're going to be here at our current position. Now the rule is as follows. If land is seen, the captain sees land, the search for the captain immediately pauses and transfers over to the first mate. And the first mate will look at that island in its entirety before coming back to the captain, and the captain can then resume their search. So essentially, finding land will cause the captain's search to pause and the first mate to begin their own search. So let's go through this example here. We're going to assume the same search order here with NESW. I'm going to start here at our @ First we add north. In this case we have 20. So 20 gets added. Then we look to the right and we see 31. Well, 31 is very different because 31 is actually a land tile. It's represented by this lowercase o here. So we're going to pause the search here. We still have to store this data so we can come back to it, but we're going to pause the captain search, transfer over to the first mate. The first mate essentially lands here at position 31 and goes and searches this island for the treasure. So the first mate ends up dropping down to 31. Now the first mate is going to look through land and essentially only look at land positions. If he sees water, he's going to ignore it. So we're going to go here. So it turns out that the last 30 minutes of my recording from my previous session kind of corrupted, so essentially everything was lost after this point with the land example, so I'm just gonna redo it right now. So back where we had this map here with a 4x4 that has the @ here at the very bottom left corner, the treasure here at the upper right corner, but in this case we have two small islands we can see right here. And essentially, this kind of makes our search a bit more difficult because not only do we have to do a captain search, because the captain essentially only looks at water locations, we also have to consider the first mate as well, because the first mate is responsible for looking on islands if the captain ever encounters land. So let's go through this, and before I do, I just want to make sure I'm recording so I don't lose everything. Alright, we're good. So let's do it. So before we have captain that uses a queue, first mate also uses a queue. So first, we're going to start with the captain. The captain is, the ship always begins in a water location per the rules of the specs. So we're going to consider our current location as our starting position, which is 30. We're going to look in the order we had before, which is north, east, southwest. This is the default in the case that no search order is given, but as I'll mention later, this will be passed in through the command line if the user wants to use a different search order. So we're going to look to the north first. We're going to see, okay, we can add 20 because that's a valid water block that has not been visited yet. We can look to the east, we see 3-1. 3-1, however, is not a water location. It's actually a land location that has not been visited yet. So as a result, we'll have to stop the captain search as of now. We're going to pause it, and we're going to drop the first mate off at position 3-1. So now, notice here that once we saw this land location, we just immediately stopped the captain's search. We're not going to go through the rest of the positions, the adjacent elements 2-3-0, or the starting position, until after the first mate finishes looking at the island in its completion. So we basically passed control of the search from the captain to the first mate. So now the first mate is going to use its own container. So in this case, they're using a queue. They could very well be using a stack because the first mate does not have to use the same container as the captain. But in this case, we're just using a queue. So we're just going to begin our search normally, but only on this island, as if we were doing with the captain, right? So in this case, we're looking at the first mate. So we're at position 3-1. Our current is going to also be position 3-1 because that is our starting position. We're going to take 3-1 off the queue, and then we're going to add elements adjacent to 3-1 in this search order here. So we're going to look above to the north, we see 2-1. 2-1 is a land location that has not been visited yet, so that's fine. Look to the right, we have 3-2. 3-2 is water, so the first mate doesn't care about water, so 3-2 does not get added at all. Look to the south, there's nothing. Look to the west, there's water that's already been visited. So the only real tile we get to add here to our queue is 2-1. So now we're done with this. We can look at our next element in the queue. In this case, it is 2-1. So we take 2-1 off the queue. And now we're looking at 2-1. We look to the north. 1-1, that's a water tile, so we ignore it. We look to the right. 2-2, that's a land that we haven't visited yet, so we put it on the queue. Look to the south, that's land that we visited, so we ignore it. And look to the left, that's water that we visited, so we ignore it. So now we're done with 2-1. We now look at 2-2 as our next element in the queue. Now notice here that with 2-2, regardless of which direction we are looking at, none of these are valid to add to the queue because it's either water or has been visited already. So as a result, we don't add anything after looking at 2-2. And now our queue is empty. And if the queue is empty, it indicates that we did not find what we wanted to find during the search. So in this case, the first mate did not manage to find the treasure here in this lower left island here. So as a result, because the queue of the first mate is empty and there's no treasure that is found, the first mate essentially just returns back to the captain at the location where he was dropped off. So he's returning to this captain here, and the captain can now resume their search. So the first mate is done, didn't find any treasure on this island, and basically is going to pass control back to the captain. The captain is going to resume looking at the next element. So before we stopped off and looked at the island, we were in the middle of looking for adjacent elements around 2-0. Well, 3-0, right? So we added 2-0, and we added 3-1, but 3-1 was a land position, which triggered the first mate to look through this entire island. But now that we're done with that, we can continue on. We can look to the south, nothing there, and look to the west, nothing there. So now we're finally done with 3-0 as our current position. We go to the queue. Queue is not empty, so we can continue looking. Next element in the queue is 2-0. So we're going to add 2-0 as our current. And then now we're going to look up. We can say, okay, 2-0, 1-0 to the north that we can add because 1-0 is a water location that hasn't been visited yet. 2-1, well, that is a land location that we haven't visited yet, but the first mate has visited. So we ignore that. We don't drop the first mate off again because we know that the island that's associated with 2-1 has already been visited by the first mate. Similarly to the south, we have a visited tile, and to the west with nothing, so only 1-0 is added here. Now we can look at the next element here, which is 1-0. 1-0, we look to north, we can add 0-0, that's valid. We can also add 1-1, that's also valid. The south and west, there's nothing, so we're done here. Next up in the queue is 0-0. 0-0 to the north, there's nothing. To the east is 0-1. so we can add 0, 1. Southwest, there's nothing, so now we have 1, 1 as our current. 1, 1's gone from the queue. 1, 1, we can look to the north. Can we add 0, 1? Well, 0, 1 has already been visited, so we don't, but we can add 1, 2, because 1, 2 has not yet been visited. South, there's nothing. West, there's nothing, so we're done with 1, 1. Now the next element in the queue is 0, 1, so we take 0, 1, set that as our current, add adjacent elements. To the north, there's nothing. To the east, there's land. And once again, now we've hit another land spot that has not been visited yet. So we're going to pause our search from the captain. Once again, we're going to transfer control down to the first mate by dropping them off at this island to begin their own search. So now the first mate essentially gets dropped off at position 0, 2, because this is where we hit. And now the first mate is going to now look through their own queue to determine if there is treasure on that island. So current is position 0, 2. Now we're going to add all adjacent elements to 0, 2 to the queue. To the north, there's nothing. To the east, there's 0, 3. So 0, 3 is added to the queue. But wait, 0, 3 is actually the solution because we found the $ here, which indicates that the treasure has indeed been found. And because the treasure has been found, we can stop everything. Our job here is done. So here we go. Let's add this arrow here because we found 0, 3. Our job here is done. Now we can return the path that we followed to get here. So in the case where captain and first mate both use queues, we can see that the path we followed, we got here from this, and we got here from this. So essentially we follow the arrows back using back tracing. We end up getting something like this, where we move along this edge here, the left edge, moving up and then moving to the right on the top. So this is the correct solution that we get. Now, what do we actually print? Right, so we've covered, how to actually determine the path to the solution, but what do we actually want to print out? Well, that depends, and the reason why I say that depends because the way you print stuff out depends on what flags are passed in through the command line. So under normal situations, I'm going to extend this a bit. If nothing is passed into the command line, if your program just runs normally without any flags, then you should just print out basically whether or not the hunt succeeded or not. So for example, if nothing is passed in and the hunt succeeded, all you really have to print is essentially just, a statement that says whether or not the hunt succeeded or whether or not it failed. So it could be something like, treasure found at some location like 0, 3 with some path length. So with path length 6, for example. This is the solution for the previous test case here. Or if it failed to find a treasure, you would print out something like no treasure found after investigating some number of tiles, right? So basically, let's just use 281. So after visiting 281 locations. All right, so this is something that you would print out normally without any command line flags. However, the user might specify different flags to tell your program to print even more information. And this might be needed in case the user needs to debug information or if they just want a more detailed output from your program. And a few of the flags I'll mention here. This is something you have to look in the specs for more details about, but I'll just go through a brief, quick overview of what these are. So first one is V, which stands for verbose. And this essentially tells your program, say, hey, instead of just printing out the solution, print out the steps you did to get there, right? Not just where you found the treasure or what the path length is, but also like the process. So not only do you have to print out where your hunt started, right? You also have to print out where the first mate was dropped off. So basically which islands at which positions were they dropped off. And also you also have to print whether or not the first mate found treasure on each island. Yeah, this is something you have to read in the specs for, but essentially you'll have to print out additional details for each island that you visit. So in this case, with this, you would say, hey, I started here at 3-0. First mate got dropped off at position 3-1. tried to look through the island, did not find anything, so we return, continue along this path. First mate got dropped off again at position 02, and then was successful in finding the treasure at position 03. So that's essentially what the verbose mode tells you to do. Another mode that you could have is stats mode, and stats mode is identified with the S flag or double dash stats. And essentially for stats mode, you'll have to print out statistics about the hunt, and this includes things like your starting location, number of water locations investigated, number of land locations investigated, how many times the first mate was dropped ashore, the path length, all those details. This is something you'll look in the specs for, but essentially the stats mode would tell your program to print out different stats, and your program will have to consider these. And when you're implementing your program, you must be able to keep track of this information in case the user decides to ask your program for the statistics. So there's that, and there's also the P flag or the show path, and essentially this tells your program to actually print out the map, right? So if the captain or the first mate actually want a map to the final destination where the treasure is, this will tell your program to do that. So for example, if you're told to print the map after your solution, you might have to print out everything where you can get something like this, right? So this is just, I'm not sure if this actually matched the above example, but just something like that. So basically, in the previous example, we followed the path up to the top left corner and then we turned right. And then, I'm not sure what this map looked like, so I'm just gonna randomize here, but essentially what you're going to have to do is you're going to have to print out the solution by altering the map we give you an input file and printing it out such that the path that was taken gets replaced with characters such as this, a horizontal bar, a vertical bar if it's moving from top to bottom, a left to right horizontal bar if the path goes from left to right, and a plus sign for a corner. So essentially you'll be using these three characters to map out the path to the solution where the treasure is replaced with this X symbol. All the other characters are not modified at all. So if a tile is not part of the solution path, you don't mess with it and you just print it out normally as it was in the original map file. If it was a land location, it would just be a lowercase o. If it was water, it would just be a period. So there's that. You can also print, so this is printing for map, right? You can also print a list. And the list essentially is the same thing, except for you're printing out the coordinates that you visited. So for example, if you start at position like 50, and then you move down to like position 40, and then you went to 41, and so on and so forth. You hit an island at 42, and after the island, you did the search on the island. So you did the search on the island, 43, and then you found the treasure at 33. You might get something like this, right, for list format. This is something, again, look at the specs for the specific details on how to output this. But essentially, print map, print list, you just print out the solution file either by, illustrating the path visually on the map file we give you, or printing a list of the coordinates that you visit along the way. Fewer things, I guess they'll mention since we're here. We have -h, which is help. Essentially just print out a help message and exit the program for the user. We also have -c, or captain. And that essentially, you can change the searching algorithm that the captain uses. So you can specify, captain with the word Q after it if you want the captain to use a Q. If you want the captain to use a stack, you can specify stack at the end. You must include one of either stack or Q after the C flag or the word captain. Otherwise, it's an error and you should probably catch that. Similarly, you also have F, which is the first mate's flag, and you can use this flag to set the container that the first mate uses to do the search. Once again, -FQ means the first mate uses a Q. -F stack represents if the first mate uses a stack. Lastly, we also have something called the hunt order, which is determined using the O flag. Hunt order essentially tells your program, the order in which elements are added, right? So in previous examples that we used the default, which is north, east, southwest. So basically, if we were at this certain location here, we would add this tile first to our container, then this, then this, then this, right? But we can also specify different order, right? We can use like SCWN, and that we would just add this first, then east, then west, then north, right? So your program will have to handle that. A good way to do this is you can take the string that is passed in, essentially turn this into a string, and look at the characters individually at index 0, at index 1, at index 2, at index 3 to determine which way to go. But that's something you really have to implement on your own. Hunt order is just essentially telling your program the order in which elements are added. Guess a few more details I want to mention. I'm not sure if this was part of my recording that was cut off or not, but your program can accept two different types of input. You can accept maps, right? So maps would essentially be, something we've shown before, where you get like kind of a 4x4 grid in this case. So M stands for map, 4 stands for dimensions. It's always going to be a square. You're going to end up getting some like nice picture-ish form of a map here. So here's an example like that. So here's a map that you could be given. That's a valid input file. You also can be given a file in the form of a list, and that's specified with the L as the first character. And a list is essentially a list of coordinates that represent the map. So instead of getting this nice picture-ish map that is all nice looking, you also have a list which would just pass in the coordinates as well as the type of terrain that coordinate has. So in this case, at position 02, we have land. Position 03, we have, the treasure. Position 1-1, we have land. 1-2, we have land. 2-1, we have land. 2-3, we have the @ symbol. 3-1 is land, and 3-3 is a land. And in list mode, all positions are not included. So in this case, 0-1 is not included in here, and that's on purpose. All positions that are not included are generally assumed to be water. So everything that's not in here is a water tile. So that's list format. One last thing, I guess, is the containers that you can use for this program. All right, so a lot of this is identifying which data structures to use in order for your program to be most efficient. And let's be honest here, for stack mode, if you're doing a stack search, you should probably use a stack. And if you're doing a queue search, you should probably use a queue. Now, I do want to mention here is this is not the only way you can do this, right? You don't have to define both a stack and a queue to do a search and say if the user wants me to do a queue search, I'll run this section of code that uses a queue. Otherwise, if they ask for a stack, I'm going to run this exact same portion of code that instead uses a stack and just copy and paste everything. You don't have to do that. There's another data structure called a deck, which you probably covered in lecture. A deck is essentially a stack and a queue in one. Alright, it's one data structure that covers both the functionality of a stack and queue. In a stack, you can only push and pop from the same end. In the queue, you can only push and pop from different ends. But deck removes this restriction and says you can insert and remove elements from both ends. So in a deck, you can do push back normally to add an element to the back. You can pop back to remove an element from the back. But you can also push front to add an element to the front. Or you can pop front to add an element, pop an element from the front. Now, one thing you have to realize with a deck is that because it removes the restriction with a stack and a queue that you can only add or remove from the same or different directions, you have to be more careful with how your program is implemented to make sure that you're actually adding and removing from the correct end. So if you're trying to have your deck emulate a stack, you should push and pop from the same direction. So your deck should only support push back and pop back, right? You should not be pushing or popping from the front. And if you are, you shouldn't be pushing or popping to the back, right? In a stack, make sure all your pushes and pops are in the same direction. Similarly, if you want your deck to behave like a queue, you must make sure that your pushes and pops take place on opposite ends of the container. So instead of, if you want to add an element, sorry, can't spell today. If you want to add an element, make sure you call deck push back. If you want to remove it, make sure you call deck push pop front, or vice versa if you want to, switch it around. But just make sure for a queue that you're inserting and removing elements from different ends. So that's essentially the gist of project 1 that this video should cover. Good luck on the project. Please start early. The most difficult part of the project is, for a lot of students, time, right? And being able to start early will give you the opportunity to not only, finish the project earlier, have more time to do optimization, find bugs, but also gives you more time to come to office hours, get the help you need, and not have to wait, 2 hours just for 5 minutes of help, because it's going to be inevitable that, as the project deadline nears, you're going to end up with 60 or 70 people in the queue, and it's just not feasible for even our larger staff this semester to take care of every single student. So please start early. Get this thing done as soon as possible, and if you have any help, definitely come to us. We'll be more than happy to help you with this project. So that should be it. That's the end of this video. If you have any more questions, feel free to post a comment here or on Piazza, which I'll probably link the video to. I'll be probably watching the comments to this video to see if any clarification that I should make. If you find an error, definitely let me know so I can, correct the error and let people know as well before they follow this tutorial incorrectly. But thank you so much for watching. Best of luck on the project, and I look forward to a great semester with all of you.